Yeah. So now we look into human eye. Like noise, viewing is also related to human, it's the same thing. They have processing of the images at the brain, and therefore some subjective issues also. Sensitivity depends upon not only wavelength, there are other issues also. So let's quickly look at this. This is a transducer. Again, the light energy it converts into electrical signals and then goes to the brain. So you have we'll quickly look into this. We wouldn't go too much into the physiology part of it, like we didn't do much for the year. So you have a eyelid. You have a eyelid here, iris, pupil, cornea, and the lens. So this is the lens basically, and there are muscles here which can close. You can close or open your eyes, and then through this lens the light passes and it forms an image onto the retina, right? And then you have got some nerves here which actually converts this this optical signal into appropriate kind of electrical signal and sends to the brain, and then brain does the processing and recognizes the three-dimensional pattern, right? It does in a very complex manner. So basically is the 3D pattern which it recognizes, although in a retina it will be 2D image. So finally it is the human eye is able to see all 3D things, right? The difference between the light and the object, lighting of the object, the illumination of the object and its surrounding, everything put together. So there is some amount of beyond also physical lux level, there is something else. That's therefore in case of like decorative lighting, the total light pattern, 3D light pattern, that's very important, because that gives you the visual, that finally gives you the feeling, right? So that's what it is. So you have two types of nerves actually. We will not go much into this, but two types of nerves, one's called cones, others are called rods, and you have what is called photopic vision and scotopic vision associated with them. So this particular one, the rods, their sensitivities with the wavelength is something like this, and for equal energy, for example, and for cones this is the sensitivity. So you can see somewhere here the eye is most sensitive, around this zone, somewhere 500 to 600, between them eye is most sensitive. That's actually where the sunlight is also maximum. The quantity of this proportion of this color is maximum in sunlight. So we don't go into the details anymore into this physiology aspect of it, but what is important for us is to know that it is not the object light alone which is required for comfortable vision or comfortably visual comfort. The surrounding light is also important, right? So you have some angular range, right? So we have a binocular field, that means both eyes sees together. Other animals, like one eye is here and one eye is there, they don't have binocular vision. Many animals don't have. For example, many of these birds, you will see that they actually, or even cow sometimes wants to see details, something cow, or they don't have binocular vision, but human binocular vision. So this is the overall binocular field. This is the central field where you are focusing, and I can focus. It's a system, intelligent system. It can change its focal length, and you can see the near object or far object. This opening can be adjusted. This opening can be adjusted. This opening can be adjusted. Aperture for a camera, aperture can be adjusted, right? And so that too much of light or less light you need. So you go to it's too bright an area, actually aperture will get reduced and it occurs. So it's an intelligent system. Anyway, so it senses the surrounding and then accordingly it adjusts itself. So this is the main binocular, this is the main field what you are looking at. Within 30 degree you see 30 degrees of vision side. This is the main field. Then the left eye alone can see this portion, right eye alone can see this portion. So between this 60 degree here, totally 180 degree, this total 180 degree, but you don't see everything. You don't see everything, but you see something where you are looking at directly, right, what you are looking at. So this is that 30 degree which you are focusing on, and even if you are looking at this, something happens from, something comes here also, something here, although you may not be concentrating on that, because finally the processing is important. So that's what it is. So we define certain things. I mean, how much light do I need in order to see a thing? It depends upon the size of the object. So we define certain terms. For example, visual acuity is defined with respect to the smallest size of the object I can see. I am doing reading, let us say if I am reading, then possibly I keep it a fixed distance from my eye, something like 25 centimeter. That when you go to an ophthalmist, they put one thing says how good you are reading at the, your eyes are good to read the close objects, and then looks at the long vision also. Now visual acuity is related to how, smallest size object that you can perceive. Supposing the size is less than 1 millimeter, some details are there in 1 millimeter, you won't be able to see. Distinction will not be there. So visual acuity is reciprocal of the size of the smallest perceptible detail in a given environment, given visual environment. That will depend upon the lighting level. Young people like you, you might be able to see things without much light, normal 20 to 60 adult, they will be able to see things with much light. But if you are not able to see, what you do? You increase the light. So capability of the eye to see is a function of the lighting level. That's what we are trying to look at. So if I have a visual environment, whether I am able to see it or not, or the smallest detail that I can perceive, that's a function of the lighting level. That's a function of the lighting level. So if I want to decide how much lighting level I should add, it will depend upon what smallest size of the object I want to perceive. So if I am reading, the smallest size is a letter. If it is English, maybe small I or small o, that would be the size of the letter. But then it depends, if I want to read, I will keep it at a close distance. If I want to see something different in a blackboard, or the distance would increase. So it is related to the distance and also the size. So size we talk in terms of angle, it subtends on the eye. Size because that will be the dimension of the object divided by the distance. So size here we talk in terms of angle. So size, for example, A, this A here, this is the size. The size will be this distance, this height divided by, this size divided by length divided by the distance. Here, for example, this length divided by this distance. So size is talked in terms of dl by delta L by R. Size we talk in terms of the angle. Size we talk in terms of delta I by R, and we define it by rho, the angle, and visual acuity is 1 over rho. Visual acuity is 1 over rho. Visual acuity is 1 over rho. What is visual acuity? Size of the smallest perceptible detail. smallest perceptible detail, right. So, size here we define in terms of angle, and smallest, delta L is the smallest length that you can perceive. So, if you are talking in terms of a letter you are reading, that will be possibly 2 millimeter, least size of the word that you read in a book, 2 millimeter, and you keep it at a distance of about 25 centimeter. So, 2 millimeter divided by 25 centimeters, 250 millimeter, that would be my rho, that would be the rho, right. So, 1 over rho. So, if 2 mm I am able to read, then 1 over rho will be, if that I am able to read, but 1 millimeter I will not be able to read. So, smallest perceptible detail that I can read in a given environment, I call it visual acuity, right. Visual acuity is the size of the smallest perceptible detail in a given environment. So, it is a function of lux level. If I increase the lux level, visual acuity will increase. I can see smaller and smaller object, but you see that of course, this is the rate at which I can read. I will talk about this sometime, right. This is rate I can read, what is called performance. Performance is the rate at I can read. You are asked to how fast you can read this, how fast you can. So, that will also depend upon lighting level. That will also you will take can't read it so easily, so you take longer time. But if you are able to read it easily, then so performance is related to that, the rate 98% in some scale. So, you can see that visual acuity increases with the lux level, but initially increases at a faster rate, then somewhat reduces down, right. So, lighting level is important, acuity of acuity versus illumination. So, acuity increases with the illumination level. So, I should increase the illumination level. So, the illumination level I required for watch repair would be quite different for that I would require for reading, because the distance is important, but then the finest details that one is looking at it would be different than like possibly I am doing some other job, maybe something like not reading, separating some removing my papers from my table, one piece another, and things like that. That would require much less level of lighting. So, that you can understand, right. So, this is one thing, but that is not all. As I said, my central field is only 30 degree. Surrounding next to this is some places I have monocular right vision, monocular left vision, but contrast is very important. If it is all equally bright, you won't see anything. So, if you are making PPTs, transparencies, and you want to make it very decorative color, and you use yellow or white, you won't see anything. The person wants to read, can't read. So, black or blue, dark blue and black on white background, that is what is easily. So, the contrast between source or object and its surrounding is very important. If you do not maintain a contrast, you do not see that. If you do not maintain a contrast, if this background of my slides are all yellow, and I just put again orange on top of it, you won't see anything. So, quite often people do this kind of mistakes, particularly when you are a student and things like that, doing it not many times, first time or second time, then you like the color, but actually colors should be only used. The contrast is important, black and white or deep blue and blue. Color should be used for only for the purpose of if you want to emphasize something, right, want to make a distinct thing. So, one line to another line you might have a color, but use blue and black. So, contrast is very important, contrast sensitivity is important. You can, so what is the least contrast you can identify? Maximum contrast anyway I will see better, but the least contrast I can identify is important. So, contrast sensitivity is the least perceptible contrast in a given visual environment, least perceptible contrast in a given environment. So, what is seen is actually we define it in some manner like this. Contrast sensitivity is defined at B0 is the object brightness minus brightness of the surrounding, because black letter on white background, white paper, black print on white. So, white is the surrounding, black is the object. So, difference between them is this, right, or if it is black paper, white letters, then also the same thing, divided by the brightness of the surrounding. That is what we call contrast sensitivity, or some places you might find that minimum of this is taken, because I can have black background, white object, or white background, black object. So, contrast sensitivity is defined like this, difference between them divided by the least of the two, right, and least contrast you can perceive in a visual environment, it is better, right, because you see I am talking of blackboard and book, that is fine, but not always it is blackboard and book. If you are doing something, some task elimination, somebody is doing a surgery, so body's color is not what you want, the contrast will not be what one would be wanting, right, the human body or whatever it is. So therefore, how much lighting level do you need, or for the least contrast that you can perceive. So, light, that is what we are saying. So, contrast sensitivity is related to least contrast I can perceive, the difference should be least. So, this is seen that if you increase the average illumination level, average brightness level, the contrast, least perceptible contrast, least perceptible contrast, because it is expressed in percentage ratio, difference between them, difference the least is B0 minus Bs, right, B0 minus Bs. So, smaller becomes B0 minus Bs divided by Bs, that is what the equation was. So it can be expressed in percentage, So, as I increase my brightness, as I increase my average brightness level, the smaller contrast I can actually perceive. I can perceive smaller contrast, but beyond a level it starts actually. So, there is an optimal level somewhere, right, average luminance level in candela per meter square. Beyond a point, I mean, you increase the brightness too much, everything becomes equally bright. You increase the light too much, everything will become, after all, the reflection, when we talked of value. So, what you see is also depends upon, if you put too much of light, reflectivity, or both can become very bright, and you do not see contrast at all. So, as a result, contrast sensitivity, there is an optimal brightness level, or if you see it in this manner, brightness of the background in candelas, contrast sensitivity in percent. So, it is in apostille actually, this is in so he puts in apostille to candela, that is why 1 by pi. So, it increases, contrast sensitivity increases, but becomes steady, defined in a slightly different manner, not exactly using this formula, slightly one, is 1 minus that. So, contrast sensitivity increases, right, because here it was constant or reducing down, here it is showing that it is constant. So, there are some experiment some people have done, but the point that we take is continuously increase of brightness level may not give me a better contrast sensitivity results. I may not be able to perceive the lower contrast, difference between the two would actually I may not be able to perceive. Performance is related to speed, rate at which you can read, right. So, time required to read, say it is in some sort of ratio. So, you have standard number of words or letters. So, at what rate you can. So, qualitatively we understand. So, performance is rate, contrast sensitivity is difference between the object and the surrounding, their brightness difference. I should be able to perceive the least difference, and other one is the size. Performance is rate. So, all three are called visual efficiency, all three put together are called visual efficiency. So, visual efficiency, performance So, it is a time. What we have seen is again this one increases, but does not, you can't see time to read a fixed number of word. So, after that it does not reduce number, supposing I have a fixed number of letters or words standardized which I want to read. If the time required to read this initially increases, initially decreases as I increase the lux level, but beyond a point it does not. So, all that point I am trying to make is that increasing the lux level in the room very large amount, I mean just continuously does not make much sense. While visual acuity increases somewhat, performance level may increase up to some point, then I mean beyond that it does not improve, and contrast sensitivity also improves up to certain point, beyond that it does not improve. So, there is an optimal lux level for every type of task, optimal lux level for every type of task, and that is given in the code or similar sort of situation, but there is a formula. So, visual performance is speed of seeing in some relative scale, and visual efficiency is all three of them. So, visual efficiency improves with lux level, but do not improve continuously. That is what qualitatively we should understand, all right, qualitatively we should understand that, and therefore, there is an optimal lux level for every task, optimal lux level for every task, and that is given in the code, that is given in the code. So, quantity of light, its distribution, all right, this is important, and I think there is a formula, and I hope I have kept that formula, yeah, there is a formula. So, I will come back to this statement later on. So, required illumination is given by this formula. Required illumination for a given task is given by this formula, where R is the highest percentage reflectance of all the details, highest reflectance, right, because it will depend upon reflectance of this one, whatever light falls in, how much it comes out, and S is the size of the critical detail. For example, I was talking of the word, if you are reading, so size would be in terms of angle, actually size will be in terms of angle, it is given in this manner, delta L by R, and 3435, these are conversion, unit conversion, etc., in terms of radians, because 19.34 is also a kind of an it is a unit conversion. So, E is the illumination required for a size which is given as the smallest length. Supposing you want to read word in a book, delta L is the length of the smallest letter or least dimension of the smallest letter, R is the distance at which you want to keep your book, and this is for radians and equivalent conversion in minutes, actually it will be in minutes and all those. So, some unit conversion term, and this is 10 to the power 4 lakhs, this multiplied by this gives us 10 to the power 4 lakhs. This is the reflectance of the details, is the highest reflectance. In other words, if it is white and very clean white, new paper, not old paper, old paper tends to lose their color, this would be possibly close to 1. In old paper it would be, and black print. So, old paper it would be somewhat lesser, and this value is given in terms of lux, this value is given in terms of lux. So, one can calculate this out depending upon task. So, in case of watch repair, this size will be different. In case of seeing, now you can think in dramatics, facial expressions 22.5 meters, so things are different, or if you are seeing blackboard, things would be different, surgery it could be different, right, office it could be different. So, depending upon the type of task, the sizes will vary, and reflectivity of the detail will also vary, one can do. But then this calculation you can do, this is the basis, values are given. Most of the code gives you this value. For example, you know that in classroom general lighting level should be 150 lakhs, right. So, this is given in codes, most of the codes, illumination codes or building codes will give you these values. So, this and this statement I did not make so far, I am going to make this. So, you have to have illumination level as desired, you have to have illumination level as desired in a given space, right, as desired, and this is calculated, basis is this, the values are tabulated, and you use the tabulated values, right, you use the tabulated. For example, in corridor it would be different, in your working plane, on the bench or table where you are writing it would be different, and somewhere it is around of the order of around 300 lux for reading or similar sort of thing, maybe general corridor etc. 150 lux for where I want to walk and see, and these values are given, right. Now this statement I did not mention. The important thing is distribution of the light is important. Only on the task if you keep 300 lux on the table and surrounding is not good, the contrast could not be, the brightness. So its distribution is important. Not only the object, its surrounding is also important. Next thing, it should not be, there should be no flicker of light. If it is artificial illumination, no flicker. Flicker is uncomfortable. Flickering should not be there as far as the lamp is concerned. Well, if it is of course that kind of effect you want to get with a strobo in a stage, that is a different thing. In drama they use, of course in dance like Michael Jackson's, they would use strobo, dark doom, dark dim, whatever it is, or in drama sometimes they do it, like some ghost dancing and things like that. So somebody on white, making all sorts of things. So strobos, that's a purposeful flicker, that's not a problem, but otherwise, if it's artificial lighting, flicker should be avoided. The next thing is glare. Now I am not sure if I am defining glare. Yes, I am defining glare here. And what is glare? Glare is when too much light falls onto your eye, you don't see anything, just don't see anything. Somebody puts a torchlight onto your eye, you don't see anything, right. So that's actually called disability glare. You just don't no ability to see. So this disability glare. But we are not much interested in disability glare. Anyway, in a classroom or in an operation theatre, the doctor is not going to put light on the person's eye itself. So disability glare is not the thing, but there is something called discomfort glare. Discomfort glare comes from the contrast difference between the object and the surrounding. For example, some classrooms, where like blackboard and there is a window there. Blackboard is on the corner. You don't see you can't distinguish them, the letters in some corner. You just don't see them. Or even if you see, you have to really struggle yourself to see. That's called discomfort glare. So disability glare, light is totally scattered. It doesn't form an image in the retina, right? Too much of light coming in, it doesn't form an image. It gets, so it actually scatters like headlight of a car coming in. People driving. This people driving in this campus or small areas put their what you call high beam light in the night. That should not be done. I am sorry that this kind of driving culture is not very good. This will not happen, but in highway you are supposed to, because there is no light and you want to see the longer distance. So, it's a high beam, it throws quite off, but in local neighborhood areas, as we call it, neighborhood areas, actually you should use a dipper. You dip it down, only locally you see your front. So, that kind of a high beam, a cyclist coming from the other side or a motorcyclist coming from the other side or a car coming from the other side, they face what is called disability glare. You don't see anything, you go totally blind, right. But in a room, this is not the issue. In a room, discomfort glare is more of an issue, and this is contrast difference because coming out from the contrast difference from the source and surrounding. In the visual field, generally this is discomfort glare. This is discomfort glare, right? This is discomfort glare. Too much incident on the eye may cause disability glare due to scattering. So, this we are not interested in as much, but this is very important for us. We do not want discomfort glare which occurs, let us say, as I said, because of the contrast. For example, if you have a blackboard, white chalk written on the corner and too much light coming onto it, what happens is, because reflectivity is, even black one tends to become bright because too much light has fallen to it. So, contrast reduces, so you do not see. So, this is what it is. So, there we define something called glare constant, and there is an empirical formula which relates it to the brightness of the object and brightness of the surrounding, right, ratio of brightness of the object and brightness of the surrounding, and the formula given is something like this. It is an empirical formula. B0 is the object brightness, Bs is the surrounding brightness, and this is something related to your position, because light might be coming from somewhere else and your viewing might be, the object might be somewhere along another distance. For example, say the screen here, if there was a light focus from somewhere there, or the light that is here, if it is focused towards the screen itself, right, that can cause glare. You are not looking at the light itself, but you are looking at the object where the light is coming from somewhere, the source is somewhere, which is making an angle with your eye as well as the object that you are looking. So, that is the position, relative position of your object with reference to the light and you, your eye. So, that is called, that depends upon that position, and this is size of the object, size of the object in solid angle, size of the object in solid angle. So, this is a empirical formula. Omega is the size of the object. This is a constant because of unit, because the formula was empirical, so done on good subjects and etc., and this was must have been done in the FPS system when they wanted to convert in. So, this is related to unit, and K is 1 in apostille when it is lumen per feet square. So, when it was lumen per feet square, K is equals to 1, K is 0.24 for B in apostille, B in apostille, right, for B in apostille, all right. So, that is glare. I think we will look into this, we will we'll break for a while. If you have some questions, we'll answer, and then we'll look back into the glare, this why this 1 and 0.24 more in details.